Ceva's theorem, one of the most elegant results in triangle geometry. Named after the Italian mathematician Giovanni Ceva. It answers a beautiful question. When do three lines drawn from the vertices of a triangle all pass through the same interior point? These lines are called Cevians. Let's find out. The theorem statement. Let triangle ABC be any triangle. Let D be a point on side BC, E on side CA, and F on side AB. The three Cevians AD, B, and CF are concurrent. That is, they all pass through a single point P. If and only if the following product of ratios equals 1, F over Facebook, times BD over DC, times CE over EA equals 1. Let's watch this build up step by step. A crucial detail. The cyclic order of the vertices. The three ratios must follow a strict order around the triangle's boundary. Starting at A, we move to F, then B, then D, then C, then E, and finally back to A. Watch the arrows trace this path around the perimeter. Each ratio compares two consecutive points on the same side. Reversing any single ratio would flip the product to give 1 over 1, which still equals 1. So the convention ensures we always go around in the same direction. Example 1. The medians of a triangle. A median connects each vertex to the midpoint of the opposite side. So D, E, and F are all midpoints. That means every ratio equals 1, F over Facebook equals 1. BD over DC equals 1. CE over EA equals 1. By Ceva's theorem, 1 times 1 times 1 equals 1. Therefore the three medians always meet at a single point called the centroid. Labeled G. This is a classic and beautiful result. Example 2. The angle bisectors. By the angle bisector theorem, each bisector divides the opposite side in the ratio of the adjacent sides. So BD over DC equals AB over AC. When we multiply all three ratios together, each side length appears once in a numerator and once in a denominator. Everything cancels perfectly. The product equals 1. Confirming by Ceva's theorem that the three angle bisectors always meet at a single point. The incenter, labeled I. Proof of Ceva's theorem using triangle areas. Assume Cevians AD, B, and CF all pass through the same interior point P. We label the three sub-triangles that P creates inside triangle ABC. Triangle ABP in blue. Triangle BCP in green. Triangle ACP in red. Our goal is to prove the product of the three ratios equals 1 by expressing each ratio as a ratio of these colored areas. Step 1. Finding BD over DC. Triangles ABD and ACD share the same height from vertex A to BC. Equal heights means their area ratio equals their base ratio. BD over DC equals area ABD over area ACD. The smaller triangles PBD and PCD also share height from P. So BD over DC also equals area PBD over area PCD. Applying the subtraction rule to both expressions. Area ABD minus PBD gives triangle ABP. And area ACD minus PCD gives triangle ACP. Therefore BD over DC equals area ABP over area ACP. Step 2. Finding CE over EA. We apply the exact same argument to Cevian B. Triangles BCE and ACE share the same height from B to line AC. So CE over EA equals area BCE over area AB. The smaller triangles PCE and PAE share the height from P to AC. By the same subtraction rule, CE over EA equals area BCP over area ABP. Step 3. Finding of over Facebook. The third Cevian CF gives us the same pattern. Triangles ACF and BCF share the same height from C to line AB. Subtracting the P triangles gives us of over Facebook equals area ACP over area BCP. Step 4. Multiply the three results together. BD over DC equals area ABP over area ACP. CE over EA equals area BCP over area ABP. Of over Facebook equals area ACP over area BCP. Multiplying. Area ABP cancels between fraction 1 and fraction 2. Area BCP cancels between fraction 2 and fraction 3. Area ACP cancels between fraction 3 and fraction 1. All three areas cancel completely. The product equals exactly 1. Ceva's theorem is proved. The converse is proved by contradiction. Assume the product of ratios equals 1. But suppose the Cevians do not meet at a single point. Let A and B meet at point P'. Draw CP' extended to meet BC at point D'. Then D' satisfies the same ratio condition as D. But that forces D and D' to be the same point. Meaning CF also passes through P'. This contradicts our assumption. Therefore the product equals 1 if and only if the Cevians are concurrent. QED. The trigonometric form of Ceva's theorem. Sometimes we know the angles the Cevians make at each vertex, but not the lengths of the segments. In that case there is an equivalent condition using sines. The Cevians are concurrent if and only if sine of angle BAD over sine of angle DAC times sine of angle CBE over sine of angle EBA times sine of angle ACF over sine of angle FCB equals 1. This is especially useful in Olympiad problems where angle information is given directly. Summary of Ceva's theorem. The main result. The Cevians AD, B, and CF are concurrent if and only if of over Facebook times BD over DC times CE over EA equals 1. 2 classic applications. Medians. All ratios equal 1. Product is 1. So they meet at the centroid. Angle bisectors. Ratios cancel by the angle bisector theorem. Product is 1. So they meet at the incenter. The proof uses a beautiful area argument. 3 colored triangles whose area ratios multiply and cancel perfectly. And the trig form replaces segment ratios with sine ratios for angle-based problems. Ceva's theorem is a cornerstone of triangle geometry.